Welcome to the last topic of applications of derivatives. And after this, we are starting integration. Well, the thing is, we're starting integration right now. And somehow they always like to put this topic at the very end of the differentiation applications. That's, I would say, an American style of writing calculus books. And they usually introduce integration via antidifferentiation or antiderivatives. Let's look through this concept, which you will definitely like a lot, because at the beginning it has a lot of guessing and you will do just great doing that. So the goal of differentiation is to find the derivative f prime of a given function f. We know that. What if I want to reverse the process? The reverse process, called antidifferentiation, is equally important. Given a function f, we look for the antiderivative function, and for now we're going to call it capital F, whose derivative is a small f, right? So that means when you differentiate capital F, you will go back to the small f. But now the small f is given, and you're looking what function gave you that small f when you differentiated that function. Antiderivative definition says that the function capital F is called an antiderivative of f on an interval I if f prime equals f for all x on that interval I. Okay, let's see a cute idea I always like using in my classes. I always say, here's an idea. What if we have the speed of the asteroid approaching the Earth? Pretty dramatic idea. But say it already passed some kind of shuttle we had close to Mars or Jupiter, and that shuttle had a speedometer there. So the speed was recorded using a speedometer on that device, and we know the speed of the asteroid. And say this is the speed or velocity, and v of t of the asteroid approaching the Earth is 3t squared plus 5t minus 0.2. Now, knowing this information, can we find out how far the asteroid is away from the Earth? To know how long it lasts for us to figure out who's gonna save us, Bruce Willis or any other heroes we have. So this is the idea when we need to find the distance as of t out of the given velocity, v of t, right? That's exactly what it means to undo differentiation. Undoing differentiation means finding antiderivative, and that's what we're gonna be calling integration. Integration is the process which undoes differentiation. Yes, we can do that, and we will be doing that using antiderivatives, and that's why you call it antiderivatives, because it's undoing differentiation. Antiderivatives. So let's make a couple guesses, and it will be fun if you imagine this as a kid's game, like we see on TVs. When I ask you a question, make a small pause and you literally yell out loud the answer, because this is the fun way to do it in class. So here's a couple guesses we definitely can make right now. If f of x is 3x squared, can you guess then, oh, that's a derivative. So if f prime of x is 3x squared, can you guess then what the original function used to be? What do you think? What function we had to differentiate to get 3x squared? What do you think? 3, 2, 1. Yes, x cubed. Who said x cubed? X cubed makes sense because you differentiate x cubed, it gives you 3x squared, right? Now here's the question for you. But what if f of x was, say, x cubed plus 5? Will it still be the right answer though? Question mark. Let's check. F prime of x is 3x squared plus 0. So that's 3x squared. So that matches as well. So x cubed matches. X cubed plus 5 seems to match as well. What if it's going to be x cubed minus 1,000,000? Matches as well. Because derivative of any constant is 0. Seems like there are many correct answers, right? And this is what we're going to call a general case. Or a general solution. General case. And all those constants, we're going to call them f of x is x cubed plus c. And that c is arbitrary constant. Arbitrary. Arbitrary means any. Arbitrary constant. Arbitrary means any, random, whatever you want. So if c can be negative, c can be a pi, square root of 7, and so on. Derivative of c is 0. Check your answer. So what was the question? The question is, if f prime is 3x squared, what is the answer? We said the general case. I will do the general answer. Answer is x cubed plus c. So I'll put it in the box over here. And now I can check. And that's a good part of in the integration chapter, that you can always check yourself. You can always find a derivative and see if you was right. And when you do the exam or homework, you can actually check the answer now. To check the answer, I will differentiate what I just answered. That is differentiating x cubed plus c. That is 3x squared plus 0, which is 3x squared. Because derivative of c, since c is arbitrary constant, is 0. So we have to keep in mind this idea that even though the derivative is a unique answer, so when, this is the idea I want to point out. Derivative is unique, right? So the derivative of x cubed prime is 3x squared. That's it, nothing else. So we know this answer is the only correct answer. And that's why we could test you this before, and all the tests had one answer, and it was one correct answer. Well, sometimes simplified or not simplified. But antiderivative is not unique. So when I want to find antiderivative, then I have a family of solutions, and that's what we're gonna call. Let me just put exclamation mark over here. Close this note. And just make a definition. That's what we call a family of antiderivatives. If f is any antiderivative of a small f on the interval I, then all possible antiderivatives of small f on I will have the form that capital F we found, like we had x cubed plus c, where c is an arbitrary constant. And that's what you call family of solutions, family of antiderivatives, or family of solutions. That means integration does not give you a unique answer, and mostly because of that c. That c makes a shift. What does it mean to have x cubed plus 5 versus x cubed minus 10? That means this cubic function will be lifted up and down. Or here are two nice examples. So if I have a linear function, f of x equals x. Here it is. You know how f of x equals x looks like. If you don't, check the video where I show what basic functions we expect you to know. But this is the function f of x equals x. But if this is the answer for finding antiderivative, then we have a family called f of x equals x plus c. That's the family of solutions. Family of solutions. Why is it called a family? Because they all look like each other, but they shifted up and down by some constant. If c is 3.5, then it shifted up by 3.5. You see, here it is 3.5. 3.5. If f is negative 3, then it shifted down by -3, and so on. That's the idea. What also I want to ask you, do you know which function gave me the x plus c when I wanted to find the antiderivative? Can you make a guess? Well, just ask yourself, derivative of x plus c is what? Is 1. So here it's actually saying, when I had the original function small f of x equals 1, then what gave me 1? X gave me 1 when I'm differentiating, but also x plus 5, x minus 3, and so on. So the several antiderivatives create a family called x plus c, and so on. In general case, if g is any antiderivative of a small g, then the graphs of the antiderivatives of big G plus c are vertical translations of one or another, which basically means shifts. Vertical translations is a fancy way to say shifts. Shifts. What kind of shifts? Vertical shifts, up and down, by c. For different c, you'll have different solution. Now, finally, we can fix a notation. It's not very convenient to keep calling it antiderivative, and also it's nice to have an annotation for that. So here is a new notation. We used to use d over dx or f prime or all those notations for the derivative, right? So that's the notation of the derivative of f of x with respect to x. This WRT means with respect to. Very nice shortcut. Well, the antiderivative, or from now on we can call it indefinite integral, and the process of finding antiderivative will be called integration, will have this important notation. It will have this beautiful sign. It's like stretched S, capital S, like that, but stretched one. And it will have d with the independent variable after that. So in this case, dx, because we're integrating a function with respect to x. So the notation of the integral, this sign in front of the function, and then dx closing the function. Whatever is between is called integrand. That's what's called integrand. Integrand is the function that we are integrating. Integrand is whatever we're gonna be integrating, to integrate. Then the x part just shows me dx means, the dx part means that x in this case, dx means that x is the variable of integration, or independent variable in this case, independent variable of integration. So if we're integrating with respect to time, it will be t, then integral, some kind of function over here, any function, maybe gravitational function, g of t, and then dt. So it's always like that. You have the integral sign opening, and then the closing piece, dx, dt, or whatever it is. And that's the idea. Now I'm gonna tell you the inappropriate joke, and you should not tell it to anyone because it's not very good, but I think it always helps you to remember the notation of the integral. So that's a joke. The math teacher is going to work in passing some neighborhood where all the walls have some kind of signs and pictures on it. And then one sign says this. And the teacher stares at it and thinks a little bit and gets super angry. And he says, "Hey, how come? You should not write something like this on the wall. This is so wrong because you forgot the dx at the end." So he takes a chalk and put dx at the end. And it becomes integral of e to the x dx. That's a good joke, which reminds you, never forget to put dx at the end to show which variable you're integrating with respect to. And that's the idea. Okay, hope you like the joke. Let's move on. Now, since we have sign of integration, look how beautifully it looks like when you print it. an integral sign, then we can have some basic properties which we know from differentiation. Constant multiple rule and sum rule. Basically, since we're doing differentiation, these rules are the same. And they just say, if you are, remember when we were differentiating something like 5x squared, we knew that it's going to be 5 derivative of x squared. Same here. If you have c times the function and you want to differentiate c f of x dx, then c can just be kicked out of the integral, or maybe put back if you want. For all real numbers, c. If you want to integrate two functions, f plus g, then you actually can integrate one by one, integral of f of x dx and integral of g of x dx. Pay attention how the integral sign was here, and it has a closing element dx, just like it's supposed to be. Remember the joke. When you have the sum, now each integral sign should have its own, sometimes even different. That's an interesting idea. I will tell you later why. Should have its own closing element, in this case dx. So make sure you never forget to close the notation of the integral, or else it will not make sense when the integration is over if you forget to close it. So if I forgot to put dx at the end and now I have integral f of x plus 5, am I just integrating f of x or I'm integrating f of x plus 5? That's why you should put dx. If I put it here, then plus 5 is standing separately. If I put it after plus 5, then f of x plus 5 is being integrated. Students love integration, and I'll show you why right now. Because you will feel very smart about all of these rules, since they undo what you already knew before. Let's start with the power rule. So antiderivatives, formulas. You will feel very good right now, and then you can actually yell very loudly, what is going to be the answer? What is going to be the integral of x raised to the n dx? Okay, let's think about it. So when we had derivative of x to the 5, that was 5x to the 4, right? So what we did is we decreased the exponent by 1 and then multiplied, or maybe like this. We first multiplied by the exponent 5 and then decreased the exponent by 1. If we want to undo this process, right, we want to undo it exactly with the same idea. So the formula will be, instead of decreasing the exponent by 1 from 5 to 4, I will increase it by 1. So it used to be n, now it's n plus 1. Instead of multiplying by 5, I will divide by whatever I just changed, n plus 1. And that's a power rule. Power rule. We had power rule for differentiation. Now we have power rule for integration. Did I forget anything? Yes, I did. There's something important should be at the end, which is plus c, to include all possible families as well. Power rule tells me if I'm integrating x to the n, then the result will be x to the n plus 1 over n plus 1 plus c. I like this rule because you need to calculate n plus 1 only once. When you calculate it once, just divide by that result right away. You don't even have to simplify it sometimes. Note. What do you think is going to be happening with empty integral? That's how I call it. It's not official name, by the way, but integral, and there is no function inside, dx. Well, there is a function inside, okay? There's something inside. I just did not write it down. What is inside? 1 is inside, right? I just did not write it down. So what do you think gave 1 when I differentiated it? 3, 2, 1. Yes, you're correct. That's x. But don't forget x plus c. So just check derivative of x plus c is 1. Make sense? Remember, if you see an empty integral with nothing inside, because usually we do not write down 1 inside like this. Usually it is written as integral dx with nothing inside. Then this is going to be, the answer will be x plus c. Second formula. How about trigonometric formulas? What do you think gave me cosine x dx? And now I want to integrate that. Say cosine x is a speed and I want to find distance. 3, 2, 1, yes. Sine gave you cosine, but don't forget sine plus c. One more formula. Now, 3. What about sine? What gave me sine when I differentiated it? Do you know? Probably you're saying cosine x, but that's not true. Derivative of cosine is negative sine. So don't forget to include it into your formula. Minus cosine gave you sine and c at the end. One more formula. Told you it's going to be good. Hope you're enjoying it. 4. How about what gave you 1 over x when you differentiated it? What is the integral of 1 over x dx? What do you think? Just think about what gave you 1 over x when you differentiated that. 3, 2, 1. Indeed, it is natural log of x plus c. There's only one interesting detail to this. When I introduced to you this integral 1 over x, x could be anything, right? X is any real number. But log does not exist for any real number. X should be positive. It doesn't even exist for log of 0. So to fix any real number but not 0, actually, I would do like this, not 0, or else we're going to have division by 0, right? So log does not exist for any real number. That's why the answer for this integral actually absolute value of x. So integral of 1 over x dx is natural log absolute value of x plus c. For any x, not 0. Okay, the easy question. What is integral of e to the x dx, just from the joke? You are correct. It is e to the x plus c. Did you say plus c this time? Keep saying plus c. Then your brain will remember it. 2 more and we can practice a little bit. What is integral of 1 over 1 plus x squared dx? What do you think? Think about it. What gave you 1 over 1 plus x squared? That's a hard one. Do you remember this? Think. It's not log, but you saw this before. You saw this function before when you was differentiating something. What is that? Yes, you're right. It is arctangent. Who said arctangent? Good job. Arctangent, or tangent minus 1, x plus c. And one more question. There are much more, but I think it's good enough. I think you got the idea. How about 1 over square root of 1 minus x squared dx? What do you think gave you the function 1 over square root of 1 minus x squared when you differentiated that? 3, 2, 1. Yes, it's sine minus 1 or arcsine x plus c. It's the same thing. Very well. Let's practice a little bit and you can be ready, count to be good with antiderivatives, at least at this moment. Examples. Of course, there are much more complicated rules are coming, but at this point, I think it's pretty pleasant and enjoyable. Integral of x raised to the negative 1/7 minus 3 x squared plus 9 plus 1 over x dx. Don't forget dx. You see I'm putting parentheses like this around the function, but actually that's not necessary. In some books you will see we don't even have parentheses, because every time the integral sign starts and it ends with d and then the independent variable, which tells me with respect to what I'm integrating, we know when integral started and when it is ended. Here is the integrand, the function we want to integrate, using the properties we just learned. Using power rule first. The power rule tells me x to the negative 1/7 will become when you integrate it. So first of all, we use the property over here in the typed piece. Over here, it says if I have many pieces added or subtracted, I can put negative sign over here, inside of the integral sign, then I can do all those pieces one by one and then combine the results. So that's what I'm going to do. And that's what I call fast integration. Yes, technically speaking, you're supposed to write down the integral of the x minus 1/7 dx minus then integral. Oh, okay, once I will write it down for you, and then I will tell you not to do it again. Integral of x 1 minus 7 dx minus integral of 3x squared dx plus 9 integral of 9 dx plus integral of 1 over x dx. You're supposed to do this in your head. That's way too much writing, and usually people stop doing that pretty much after this lesson. So what I'm going to do it in my head. I know that each piece can be integrated one by one. X to the negative 1/7 will be negative 1/7 plus 1 all over negative 1/7 plus 1. That's the power rule. Power rule says if you have x raised to the constant, raise that constant by 1 and divide by the same result. Then I will have over here, I remember that this 3 can be kicked out of the integral. So I'm actually integrating not negative 3x squared, but integral of 3 integrals of x squared. Or you can remember that is just x cubed. I will do it this way. 3 in the orange color goes out, and then x squared becomes, same red color, 2 plus 1 over 2 plus 1. So you don't have to make a guess. The formula actually gives you the answer. Even though you know the answer will be x cubed, you still can use the formula, so don't stress out. And that's why this 3 cancels out, and the answer indeed is x cubed. Now, what happens with integral of 9 dx? Integral 9 dx. Two ways of thinking it. Either you take this constant and kick it out, and if you kick it out, you'll have 9 times empty integral. What is empty integral? Yes, it is x. Remember, empty integral gives you x plus c. Well, or you can rethink about what gave you 9 when you differentiated that something. Well, 9x gave you that. That's why you will have plus 9x. Check in your mind. Derivative of 9x indeed is 9. Or it's 9 times integral dx. And integral dx, I can finish this, is 1 plus c. The last piece, integral of 1 over x dx. And now we know that, natural log of absolute value of x. Now, did you try to stop me at some point and every time telling me, wait, where is my plus c part? Since each little integral gives you some kind of c, and they all might be different, they all been collected into one fat plus c at the end. That c will collect all little c1, and then c2, and then c3, and then c4 with the intermediate calculations, because they all will add up together and become some kind of number. That's why we only put plus fat c at the end. And this is the answer. Not too bad, told you. Let's try one more. And we should be done for today, for this video. 2. How would you integrate 7e to the x minus square root of x plus 31 over x squared minus 5 cosine x dx? Where my integral starts and where it ends without parentheses, can you see it? Starts right after the integral sign and ends right before the x. So that's the piece I'm integrating, and I'm doing fast integration in my mind, combining all the properties I know, all the formulas, power rule, exponential rule, logarithmic rule, and the cosine, sine, trigonometric functions. Okay, 7e to the x. I know that this 7 can be kicked out of the integral, and then I just have integral of e to the x. Integral of e to the x is just e to the x. So that's a nice part of it. You differentiate e to the x, it gives you e to the x, and you integrate e to the x, it gives you e to the x. This constant in front of it stays just like when you differentiate. So when I'm integrating 7e to the x, the result of the integration will be 7e to the x plus c. But plus c will go to the end. You can even write it down right now, not to forget. Minus square root of x, not a very convenient way of seeing it. What is square root of x? That's x to the 1/2. Then the property will be exactly the same as we had before. The power rule should be used. X, and then I will use red color, 1/2 plus 1 over 1/2 plus 1. Minus what to do with 31? With 31 to the x over x squared. Take a pencil and write it down as 31 times x to the -2, just like you already rewrote a square root of x. Then you use the same power rule. Power rule did not tell you cannot use it for negative numbers. So we will be using it right now, and it will give me 31x -2 plus 1 over -2 plus 1. So I don't even calculate it right away, you see? I'm writing it like this for you to see exactly the process. And the last one is minus 5. Why those constants are all being copied? Just because when you differentiate, those constants will be copied when they multiply. Same thing as when you integrate. Oh, also, why there's a minus here? It should not be minus, it should be plus over here. Plus 31x to the -2 plus 1 over -2 plus 1. Now, what derivative of what gave me cosine? You're right, this is sine. So it's going to be -5 sine x plus c at the end. Let's rewrite everything nicely. 7e to the x plus minus x raised to the 1/2 plus 1 is 3/2. Dividing by 3/2 gives me multiplication by 2/3, right? And it's always going to be like this. If you have a fraction, it will be flipped in front of the function. Then it will be minus 31. Why? Because it's going to be x. Let me change the color. Minus 31x. -2 plus 1 is -1 over -1. That's why this negative showed up. You can also rewrite it as 31 over x minus 5 sine x plus c. And that's the answer. I will point out that you can always check your answer. How would I check my answer? Who knows? Yes, I can differentiate the answer I got. So differentiate your answer. What is derivative of? I will even copy it for you like this. And I do recommend you to do it a couple times to check that you're not messing up with calculations. So I can find a derivative of my answer. Derivative of my answer is, so it was 7 and x here. Derivative of 7e to the x is 7e to the x minus 2/3 times 3/2 x to the 3/2 minus 1 minus, what is derivative of minus 31 over x? It's going to be plus 31 over x squared, right? Check yourself if you want. Derivative of minus 5 sine x is minus 5 cosine x. Cosine. Derivative of plus c is 0. So the answer becomes, cancel out, 2/3 times 3/2. That's 1. The answer is 7e to the x minus x raised to the 3/2 minus 2 over 2. That's 1 over, that's, what did we have before? Square root of x, right? So that's 1/2 plus 31 over x squared minus 5, that's my 5, not s, cosine x. This answer should match with whatever we had inside of the integral. Let's see. Let me go up. Here, look at this orange part over here. Does it match or not? 7e to the x matches. Minus x to the 1/2, that's square root of x. Plus 31 over x squared matches. Minus 5 cosine x. Matched. That's exactly what used to be my integrand. The part I integrated. So by differentiating the answer, you can check if your answer is correct. That's actually pretty good. Over here, I think I forgot to simplify. If you want, I can simplify this answer for you. The example number 1. X to the negative 1/7 plus 1 becomes x to the 6/7, and then multiplied by 7/6 because I'm dividing by 6/7. Dividing by 6/7 gives you 7, gives you multiplication by the reciprocal. So 7 over 6. Minus 3 cancelled out with 2 plus 1. So it gives you minus x cubed, just like we expected. Plus 9x and plus natural log absolute value of x plus c. To check that your answer is correct, you can differentiate it. And differentiation integrations are fun topics, because if I want to differentiate this piece, 6/7 will go down, multiply by 7 over 6, they cancel out each other, then x will become raised to the 6/7 minus 1, which is negative 1/7. This piece will be negative 3x squared, this will be plus 9, this will be 1 over x, and c gives you 0. And that matches exactly what we used to have inside over here in the integral. X to the minus 1/7 minus 3x squared plus 9 plus 1 over x. That's amazing. Basically, knowing differentiation, now you are almost a pro in the basic integration formulas. New topics will be fascinating as well, so stay put and be excited to watch more videos. See you next time.